Hi, today I'm doing this brief paper overview, Balancing Type 1 Error and Power in Linear Mixed Models. And basically what this paper, the reason I found it really useful is that I always struggle between what I think the random effect structure should be in a mixed model and what actually works in practice. And I'll explain that more in detail in a second, but typically I have convergence issues or other weird things come up. And this paper helped answer those questions for me. So this could be for using just a mixed model on behavioral data, or what I have actually been trying to help people with is they have longitudinal behavioral data and then they have fMRI data for a single time point. And they would like to estimate slopes over time, over say 6 to 7 time points, and put these slopes into a whole brain fMRI model to look at the relationship between brain activation and these slopes. So mixed effects models, great way to do that. You can get it to export the random effects estimate, which are the subject-specific slopes, and they tend to be more well-behaved than if you just ran a separate linear regression for each subject. So I'm not really going to get into that. That wasn't the point of this video, but that's what brought me here. And I'll show you the problem that I ran into. So this comes from this paper here. Matuschek is the first author. The last author, by the way, is the person who wrote the lmer, or the LME4 library for R. So I will be showing the R model, the model setup in terms of LMER. So if you're an R user, that'll be helpful for you. So the idea is, should you fit the full variance covariance structure, basically max out the random effects, and by that, I think I'll go over that more in a second. The basic idea is all of the within subject, if subject's your repeated measure, variables get included as repeated measures. So I, for example, often I feel like I'm restricted to only having a random intercept, which looks like this. So I have some continuous covariate x that I'm looking at, and a random intercept. And the reason I typically end up with this model is because if I try to add x here so that if x can have a variance associated with it as well, I typically have convergence issues with the data I'm working with. So I'll talk more about that too. So the nice thing about this paper is it was written with typical psychological data in mind. And basically what we have here is your standard power type 1 error trade-off. Of course, you have to be careful. So if a model is more powerful, you can only use it if the type 1 errors are controlled as well. So that's exactly what they're looking at here. And this is part of a larger conversation. You'll definitely find papers that say you need to max out your random effects structure. And this paper is saying, well, you know, if you don't, how bad is it really? And right, in terms of the power and type 1 error. So then you have to think about whether it makes sense to set a random effect to 0. So what does that mean? So in the case of, let's say we're looking at depression indices over time for people, actually that might, or whatever, something that would change over time. And you're estimating a slope for each subject, or you're not estimating a slope, but you're allowing the time effect to vary randomly over subjects. So you have a between subject slope variance. And the question is, could that variance be 0? And that's not a very realistic assumption. The other example, the data I was working with, there were four cohorts with 70 subjects each. So these cohorts are over time, so you would imagine over time the between cohort variability would be important to incorporate into the model. The problem is I only had 4 cohorts, so estimating any type of variance with just 4 things is difficult. So it's not likely the variance is 0, but for the model I'm using, I can't estimate it well. So the reason why this extrapolates to imaging data is it's very easy with behavioral data to just pop the cohort as into your random effects. But for our fMRI studies, we would have to run a 4-level analysis, you know, within subject, and then within cohort analysis, and then the group analysis would just be across cohorts, which in this case would just be 4. So it would be nice to know if my between cohort variance is small enough that I can assume it's 0, then I can do a model where I don't have to have a random cohort effect. So that's kind of one way this came up for me. And actually here's what I'm talking about. This is with behavioral data. This is over time, 2 time points. And you can see the, sorry, this is our output if you're not familiar with it, but this is the model set up here. So this is subject nested within cohort, the random intercept, and if you look down here, you'll see that the cohort variance is practically 0. So kind of lends the question, well, does cohort really need to be in the model? And I come from the school of thought that the more parsimonious model is better. So can I remove cohort? But the other school of thought is that no, with mixed models, you have to have cohort in here. And actually, additionally, I should have had time in here as well, but it's another story. So the idea is, should we be removing something from the model just because we don't have enough data to estimate it well? Basically, we know this variance probably isn't 0, so can we really motivate removing it from the model? And it typically doesn't change things, but if it does, what do we do? How do we know what's happening? So, and as I alluded to earlier, sometimes our lives can get easier if we can drop a random effect. For example, for my imaging data that I have with the cohorts, how bad is it if I don't model between cohort variance? So they mentioned this paper by Barr quite a bit, so I don't have the title here, but I'm sure if you just Google search mixed model Barr 2013, you'll find it. And they show that you're better off using the Maximal model. So include all within subject variables. They should have variance components as well. And all correlations between random effects should also be included. So the number of parameters grows very quickly. I can't remember here in the output. No. Okay. So yeah. The problem is these often don't converge in my experience. And they do discuss this in this paper as well. They say, okay, if it doesn't converge, keep simplifying it until it does, and that's what you use. So they say remove the correlations first, and then keep backpedaling. At least that's what I read. I didn't read that paper as closely, so. But then I noticed this. So this is a different application where I was trying to estimate the slopes over time. So I do have time here, so I get a random slope, and my goal was to pull out that random effect estimate and then use it with my brain data. But then I noticed the correlation between the random intercept and time was 1. So that basically means that my slopes, they're actually exactly the same as the intercepts for each subject. So obviously not helpful. And what brought me to this paper was that I was trying to figure out why this correlation was 1, and basically it happened because the variability of the slopes across subjects was so low, it's so close to 0, that this is what happened with the model. And the paper I'm covering was referenced as a paper that explains this. So in this case, by the way, what you do is you're basically done. The slopes are not going to be useful. There's just no variability between subjects anyway, so they're not going to perform well in a whole brain imaging model as a regressor. So the spoilers, these are the points of the paper. Yes, it's true that specifying the full random effect structure will preserve the type 1 error rate, but the type 1 error rate, this should say type 2, not type 1. The type 2 error rate increases, or the power goes down. So basically, this paper, it made me feel a little bit more comfortable about using the more parsimonious model. So they ran simulations. It's an experiment with 20 items that the subjects view over time. There are 50 subjects and 2 conditions. And I can't recall if each item is presented under both conditions or not. It's not matter. It doesn't really matter. And then Y is something we're measuring. For example, it could be reaction time. So the full model would look, well, actually this is not right. I have their exact full model code on the next slide, or coming up. So here's the Maximal model. So here's the Y covariate that they're interested in. 1, this is just the intercept. This is the condition, C. So C is a 0 and a 1. And then we have a random slope and an intercept for each subject, and a random slope and intercept for each item. Okay, and then this is just the data set and REML equals false. They distributed the code with the paper, so this is exactly what the paper used. And this is the more mathy version of the model. So you can see the slope consists of just the fixed effect plus the random subject effect plus the random item effect. And then you have the same for the intercept. Fixed effect, random subject effect, random item effect. And you see that we have a lot of parameters here. We have not only the variances, but we have the covariances for both the item and subject, the covariances between the slopes and the intercepts. Okay, so this is the maximal model. They took it back a notch by assuming the correlations were 0. So basically, this row term was 0, which wipes out everything. So this is model 2. And in R, it looks like this. You use a double bar, and that removes the correlation. Model 3, take it a little bit simpler. The random slope is removed for item, but we still have both for subject, random slope and intercept, but they're uncorrelated. Model 4 is the flip side of that, just a random slope for item, but not for subject. And model 5 is just the random intercept model. And again, in my experience, I often end up with this model because the other ones won't converge. Okay, so they considered two scenarios. One is that the covariance actually is 0. So what happens if we model it anyway? So the covariance they're referring to, let's back up here, is this. So what happens, for example, if I run this model when these are actually 0? Does that hurt anything? And how do the other models compare? Obviously, the model that assumes they're 0 should be best because that's how the data were simulated. So that's the first scenario. What if the covariance truly is 0, but we model it anyway? The other one is that the true covariance is small and non-zero. Oops, and. So what if we don't model it? So this is the practical application. We might have small variances. It'd be nice if we didn't have to model them, possibly. They consider different model selection criteria, AIC and BIC, and likelihood ratio tests, which you can get by running ANOVA on 2 nested models. They do not recommend using 0.05 for alpha because this isn't about false positives. They recommend 0.2 because this is a weight of model complexity. So yeah, a much higher threshold. So it's going to be a little bit harder to remove that random effect. Okay. Oh, sorry. Yeah, because if a p-value is less than 0.2, it gets to stay instead of 0.05. So here's the first scenario. The covariances were really 0. So the maximal model is actually the incorrect model in this case. Here they have type 1 error rate, and they also looked at power. So the correct model is just this random intercepts model. So obviously it has the highest power. But interestingly is the maximal model has a very conservative type 1 error rate. So the goal is to be 0.05 here. The goal here is just to be high. I don't know that they had a exact level of power that they're aiming for. Right, so that's interesting that the more complex model is actually being conservative and there's a hit in power. But again, probably not realistic that the covariance would be exactly 0 in real life. Well, maybe with the covariances, yes. With the variances, probably no. So overly conservative at the cost of power. Barr found something similar, the other reference I mentioned, and they said the loss in power was negligible, which could be true. So this is the second scenario, the maximal model, which is correct, versus model selection. So here they used the likelihood ratio test to choose the best model, going from that model, the full model, all the way to the model with random intercepts and that 0.2 threshold. And I'll show you which models it chose. So we have the maximal model on top, and then the bottom is the likelihood ratio test, backward model selection. And the goal here is the solid line, 0.05. and these must be confidence intervals on the estimates. So you can see, as we suspected from before, is that when the x-axis is the standard deviation of the random slopes. So this is not the covariance between the two. The covariance in this case was not 0, but it was quite small. But they're looking at what happens when the slopes don't vary a lot. Right, so that would be the diagonal of that matrix I showed earlier. Okay, I'm going to go back. Sorry about the flipping. So these are the covariants. So now the random slopes are small right here. Small variance. Okay. So what you see, we have a conservative model again for the maximal model until the variance gets bigger, and then actually the type 1 error is a little bit above 0.05, whereas the likelihood ratio test, the type 1 errors are actually preserved, and the power is slightly higher. It's very slight. This dotted line here is the power from the maximal model. So I don't know. I don't even know that those are significantly different from each other, but you know, power is power. It's nice to have more power. Right. So again, type 1 error controlled, power slightly better. So then they decrease the sample size from 50 to 30, and they decrease the number of items to 10 instead of 20. So now you can see the power is a lot lower than it was before, and there's a greater increase in power. So if you already have a low-powered study, hopefully your power is much bigger than 0.1. This could increase your power. It's not double, but it's like a 5% increase. And the type 1 errors are about the same as before. Actually, they're worse. I take that back. But they get out of control for the, both models actually fell out of the bounds. So what was the likelihood ratio test choosing? So this x-axis is the same. It's the standard deviation of those random slopes again. This is for 50 subjects, 20 items. This is for 30 subjects, 10 items. And you can see that the maximal model is favored as the standard deviation increases, and the intercept model is less favored as the standard deviation increases. So relating this back to what I showed you earlier, I was trying to model a random slope, and I had that covariance of 1. And that's just because the variability in the variability in the slopes was so low. So it's basically this. The maximal model wouldn't have been preferred, but one of the reduced models would have been chosen, 2, 3, or 4. So, yep. So what should you do in practice? So if your model doesn't converge, and this is in the bar paper as well, you can try adding more iterations. Sometimes that helps. And you can simplify the model by removing the covariances first and working your way backwards. And should you use model selection? Perhaps if you have a smaller sample size. Obviously, if you have larger sample sizes and your models are converging, you're fine. Just use the maximal one. And you can use the criteria that they illustrated here, or AIC, BIC. So they used a likelihood ratio test, 0.2. So what if you want to extract random slopes for other purposes, like I was just trying to do? First of all, your model must converge. Second of all, if your random slopes are highly correlated with the intercepts, something's not right. And that's what I ended up with. And it just, as I said, it turned out that the variability in my slopes was super low for the subjects. Basically all their slopes were 0. So there wasn't enough variability in those slopes anyway to probably do anything useful in another model. So basically the model, the mixed effects model being weird kind of stops me from moving forward, because it tells me that I'm probably not going to get anything. Well, the slopes were meaningless anyway, but yeah. That's all I have. Hopefully that was useful for you. I know that mixed models can be a bit confusing at times. So this is sort of the, on one end of the spectrum, maximizing the random effect structure. It actually makes it easier for setting up the model because you just dump everything in there. But this is just a tiny bit of extra work. But it's nice that they did this. It's reassuring to see that the type 1 errors might actually be a little bit better. You know, it's less conservative. You might squeak out a little bit more power. I question whether it's a ton of power, but yeah, it is what it is. So please join the Facebook group or follow me on Tumblr or Twitter, all three, and let me know what you thought of it. Thanks.